So why does it take much more energy to boil than to melt? You might want to use forces of attraction in your answer here, Mackenzie.
For boiling, you have to break the forces of attraction, and for melting, you only have to leave.
Perfect. Perfect. Good job. I've kind of hammered on that concept this year. Here you're melting, right? So, solid particles are this close together. Liquid particles, that close. Gas particles, really far apart. So to go from a liquid to a gas, you're breaking forces. You need a lot more energy. But to melt it, not as much because you're just weakening. Good job. Good job. All right. And number 4 kind of was a doozy, right? I think we're looking for delta T. So we're using Q equals MC delta T. I'm sorry, we're looking for the final temp. They give us the energy, right? They give us 1850 joules. So we're using Q equals MC delta T. Except when we plug in, Marcy, when we plug in 1850 for Q, what's the sign?
It's
Negative. How do you know?
Because it's exothermic.
Because what?
It's exothermic.
And how do you know that?
It gives off energy.
It's releasing energy, which means exo. That's the most important part. If you got number 4 wrong, it's because you forgot that right here. Exothermic, it's negative. The mass is 30 grams. Specific heat, 4.18. Delta T, final minus initial, like Laura said. So it's going to be x minus 85. X minus 85. How would we solve for x? What's the first step we would do here? A little algebra lesson here. What's the first step?
You multiply the first two.
Multiply these two together, right?
Yeah.
And then what?
And then
Did you get that number? Did anyone get that number? 30? 125.4? Okay. Times x minus 85 equals negative 1850. Divide by 125.4. Divide by 125.4. When you divide these, I think, someone help me out here. Someone who hasn't contributed yet here. Who has this? Earl, you got this?
Yeah.
What do you got?
I guess negative 14.75 joules.
Negative 14.75. Ring a bell? Someone yes? I think that sounds right to me. Good. Equals x minus 85. Max, how do we get x? Well, let's do the opposite. Right, we add it. Add it to both sides. Add it, and then that's how we get 70.25. Right, we get 70.25. 70.25 degrees. That is the final temperature. It makes sense because it lost energy. If it starts at 85, it's going to be lower at the end when it releases. Questions on that? All right, let's go over the other one real fast because I got other things we want to do here. Okay, here we go. So I'm going to read the answers, and then I'm going to talk about 76 a little bit longer here. 73. In terms of energy flow, explain why temperature of the water in the calorimeter increases. Actually, someone should answer this instead of me. Michaela, what do you think?
What?
73.
I put in terms of energy, it goes from high energy to low energy. Because copper isn't to the water.
Okay, so the energy flows from high energy to low energy, and then what about copper and water?
I just put copper to water.
Copper to water, perfect. That's what I want to see. So the energy from copper flows to the water. That's what we're looking for. Okay, 74, here we go. 50 grams of copper, 100 degrees for the hot copper. Mass of the water is 100 grams. The initial temp is 23.2, and the final temp is 26.3. Number 75, Q equals MC delta T is what you're using. It's 100 times 4.18 times, what's the change in temp? Final temp 26.3, initial is 23.2. So what is that? 3.1. And the answer to that, Kira, what'd you get? Oh, it's just a setup, right? Oh, I'm sorry. Yep, you just need to set up. So all you would need is 100 times 4.18 times 3.1. That would give you full credit on the setup, just a numerical setup. And number 76. So what error could account for this apparent violation of the law of conservation of energy? Human error does not work. I'm going to give you an example. Let's say I'm copper. And Dylan, this is fun. Dylan is the water. So I'm 100 degrees. Dylan's 20-something degrees. Now, let's say I'm holding a handful of marbles. My marbles represent my energy. So in a perfect world, if I come in contact with Dylan, I would give him all of my marbles. I would give him all of the marbles. Stay with me. If I have a hand, let's say I'm holding 30 marbles. I would transfer that to Dylan, hot to cold. Everyone agree?
Yes.
But in real life, that's in theory, in real life, I wouldn't just give him the marbles. I would throw the marbles at Dylan. Now, would some of the marbles hit Dylan and would he catch some? Maybe, but where would most of them go? To the floor, the wall, the ceiling, maybe hit Mackenzie, it would hit random people. What's the analogy? What's that analogy have to do with your answer number 76? The marbles are the heat. The marbles, the heat. What does that analogy have to do with your answer 76? Go ahead, Aaron.
Escape.
Right. The energy escapes. It doesn't always go where we want it to. Where does it go in this question? The air. Good. Energy goes to the air. So not all of it goes to the water. Some goes to the air. Where else could it go, Kaylin? The container, the cup. Very good. Where else could it go? One more. One more thing. What's in the cup with the water and the copper? Thermometer. It could go to the glass and the thermometer, right? So that, I hope, helps you understand 76, that little weird analogy. Dylan, I'm not going to throw mine today. Okay. All right. I'm going to show you a video. The video is on this thing right here. Okay? What's that called? Heating curve. So we introed this the other day. So here's what you're going to do. The video is about 3 minutes. You're going to watch the video. I'm going to give you this worksheet up here. On the back of the worksheet. This worksheet. On the back of the worksheet, you have some tasks that we're going to do. You're going to do. So this is a heating curve. After you watch the video, you should have a better idea of how to do these 5 things. You're going to label some stuff, do some calculations, then we'll go over it, and then that might be it for class because we're running out of time. So once we're done going over that, I will give you this worksheet, which is more practice with the heating curve. This is homework due tomorrow. Okay? So I'll give you that. And I got a demo that is going to be kind of playing at the same time. You'll see. After the video. So someone get the lights, please. Thank you. All right. It's a music video on heating curves. Okay, let's run. This guy, Mark Rosengarten, is hilarious. So it's pretty funny. It's entertaining. Here we go.
Molecules of solid just vibrate in the place. As you add some heat, they vibrate at a faster pace. The temperature increases nice and steadily. To calculate the joules you need, use MC delta T. But once the solid heats up to melting temperature, they start to move too fast to stay together anymore. The temperature stays constant as the melting moves along. Using heat of fusion to get joules for this ain't wrong. To melt the solid, you must add heat at a steady rate. Sounds like this changes endothermic. Don't you think so, mate? Once all the solids melted and liquid's all you got, temperature will rise once more until it gets real hot. The molecules of liquid and faster with more heat. The liquid gets less viscous and easier to beat. To get the joules you need to make the temperature to rise, use MC delta T once more, and now here's a reprise. MC delta T, MC delta T, MC delta T. lubrication is what you need, alas. This changes endothermic, heat will get sucked in. Attractive forces disappear, let gaseous phase begin. So that is how a heating curve can be made in the lab. Now you can go tell all your friends the secret you can blab. Heating stuff from solid to a liquid to a gas is an endothermic process. I hope you had a blast. If you cool the gas down, it condenses, then it freezes. If it makes it up your nose, then it might make you sneeze. Cooling down the substance is an exothermic change. The graph you get is opposite, so don't think it looks strange. So now you know all that you need about solids, liquids, gas, and how all change in phase really comes to pass. Going up in phase is done endothermically. Exothermic down in phase, I hope you all can see.
Some of that is very strange, but hilarious. All right, so pair up. Here we go. Pair up. Go ahead, move. Same partner. Your tasks are on the back.
Far out, dog.
You will need a calculator.
Above. It's gotta be above. Okay, make sure it's above. So this one, this is solid, man. This is a liquid. This is gas. Give me dog. Did you get my Jeffy dog?
Actually,
You're
Pat.
picking up what I'm putting
Pat,
down.
move up here and work with Pat. Right here. So let's choose.
Okay, so this would be
So if you are done and we're still waiting, you could start your homework. That'd be the smart thing to do. Instead of just sitting there. Laura Griffin, look at Laura Griffin. She's almost halfway done. You gotta go. Yep, I gave you the worksheet, right? Yeah. So we gotta make sure you get the answers to this classwork. When you come see me about that other worksheet later. No, this right now. We're gonna go over this worksheet right now. So but you're gonna come see me later about the other worksheets that I. Kaylee, do you need Kaylee's up?
Yeah.
Marshmallow?
If she can get out, just call over.
bam, put in homework.
Here, just do this.
Yeah, just call over your desk.
We'll just move the desk. Okay, let's stop, but we are not done. So let me make this clear. Listen up, hold on, don't move. That worksheet I gave you is due for homework, this one, okay? We're going to go over some of this worksheet. Someone's going to get to use the stylus. It's lots of fun. But let's make sure we understand what we were supposed to learn today. How this heating curve is supposed to be labeled, right? Solid, liquid, gas, melting, boiling, and then which heat equation to use. Some of that you will be asked on your homework worksheet. Okay, some of it's a little different, but you guys are prepared for it. So right now we'll go kind of right to the end. Who wants to use the iPad and show us how to label this? Because you can write on this thing here. Okay? And we're going to use purple because that's the staff color today. Okay. Who wants to label segment AB, the proper phase and the proper formula? Morgan?
I don't know, Ken.
So she's labeling AB. Who wants to do BC?
Oh, yeah.
Who wants to do BC? Mackenzie? Alright, so she said, stay with me, she said AB is a solid and you would use Q equals MC delta T. Very good. Who wants to do CD? Who wants to label CD? Michaela will. Melting, good. So she's saying Q is melting, which is Q equals M H F. Very good. So far we are correct 100%. A to B is correct. B to C is correct. So if you need some clarification, then you should not clarification, but need to fix your answers, go ahead. Okay, C to D, let's see.
Not working. Okay.
Again, if we get chopped off by the bell, don't forget that worksheet. Very good. And we will continue doing this tomorrow. DE, who wants to do DE? Earl. What I like about this is, for some reason I think it's not going to stay when I zoom out. In other words, like it's not going to stay attached to the lines, but it does because the program is pretty cool. Okay, boiling at DE, very good. Q equals MHV. Good job. And the last one real quick, hopefully we can squeeze it in before the bell. Cassie's got it. So that one is correct too, Q equals MHV. So use these notes to help you do your worksheet for homework. Gas, Q equals MC.
Oh wait, oh whatever, you guys know what it is.
Oh, well, she aborted. Whoa, that's a little violent there. So Q equals MC delta T. So that's the overall correct labeling. Again, E to F is Q equals MC delta T. Good job today. I will be after school tomorrow if you need some help. I think I have a meeting today. I'm sure I do. Bring up the calculators. We will continue going over that tomorrow.